Dear students, today we are going to study SNi mechanism. SNi mechanism is also known as internal nucleophilic substitution mechanism. This mechanism normally takes place with retention of configuration. Suppose I take a optically active alcohol and I react it with thionyl chloride, then the OH group will be replaced by Cl group and I will get a alkyl chloride. But this alkyl chloride formed will be with retention of configuration. We will see the reaction. We are studying SNi mechanism. Okay, now suppose I take a optically active alcohol. Okay, pH. Okay, hydrogen, CH3 and OH. Okay, I have taken optically active alcohol. Then I react it with thionyl chloride. I react it with thionyl chloride, that is SOCl2. Okay. Then I get the product CH3 pH H Cl, okay, plus SO2 plus HCl. Okay, these are the gases. Okay, now if you see here, the OH group has been substituted by Cl and the Cl is on the same side at which there is a OH group, and the remaining configuration of all other groups is same. Okay, the positions are same. So there, if you see here, this is the face on which OH group is attached, and on the same face the Cl group is attached, and hence it is taking place with retention of configuration. Now we are going to see the mechanism of this. Okay, so we will be studying the mechanism. Okay, I have already told you the stereochemical outcome of this reaction. This reaction takes place with retention of configuration. Now we will see why it is also called as internal mechanism. Okay. Now in the first step, okay, this is the first step I call formation of alkyl chlorosulfite takes place. Okay. If you see here, this is the structure of thionyl chloride, SOCl2. Sulfur has a lone pair of electrons. This oxygen also has a lone pairs. Attack of this takes place on the sulfur. Okay, and followed by removal of the Cl group. Okay, it's actually a nucleophilic substitution on sulfur atom. So this is the first step of the mechanism, but of course it is not a rate determining step. Okay, so we are not very much bothered about it. Okay, HCl is removed in this reaction, and what you get here is a CH3, then pH hydrogen, and here O S double bond O Cl plus HCl. Okay, now if you observe here, okay, this compound is called as alkyl chlorosulfite. Okay, sulfite is nothing but SO3 twice minus. Here one of the oxygen is replaced by Cl group, hence it is called as chlorosulfite. I am repeating, SO3 twice minus, one of the oxygen is replaced by Cl, hence it is called as chlorosulfite. This intermediate is called as alkyl chlorosulfite. Now the next step, okay, I will call it as step 2. I will circle this in bracket. Okay. This step in which this intermediate collapses is the rate determining step. This is the rate determining step, and it is the slow step of this reaction. Slow step of the mechanism. And what do you get here? Okay, these two electrons go on to this oxygen, and these two groups shift here, and you get a planar carbocation. Okay, this carbocation is a planar one, pH. This is hydrogen, and here it is CH3. Of course, this is carrying a positive charge, and this is actually S double bond O, O minus, and Cl. This is actually called as an intimate ion pair. Here the bond has been broken, but these two are in close contact with each other, and therefore this is called as intimate ion pair. This is actually surrounded by an array of solvent molecules. This is surrounded by an array of solvent molecules. Okay. Now, in the next step, these two electrons go here, this Cl minus goes here, but still this Cl minus and remains close to this carbocation. Okay. Now, in this step, minus SO2, this is SO2, okay, this is a double bond, and here what you get, CH3, pH, here H, okay, either here CH3, okay, and Cl minus and C plus. Again, this is another intimate ion pair. Okay, and these two then combine, okay, and Cl minus gets attached to the same side from which this group has departed, okay, because it is in immediate vicinity. So it attacks from the same face, and these two groups then again go out, they come out like a umbrella, okay, they come out, these three groups, 1, 2, 3, they come out, and the Cl groups gets attached from this side, and you get retention of configuration. H, okay, hydrogen, CH3, and here Cl. Okay, now you see the Cl and the position of OH. Okay, retention of configuration has taken place. Okay, now if you see here, okay, if you observe here, the rate of this reaction, okay, shall I write the rate of this reaction? Is equal to K, okay, into concentration of alcohol, okay, it was this reacted, concentration of alcohol, okay, into concentration of SOCl2. Okay, so you may reaction is rate is equal to, okay, rate of the reaction is equal to K into concentration of alcohol into concentration of SOCl2. You may think from this that it may be a SN2 reaction, but actually it is not. It is actually a SNi mechanism. Okay, and most important thing is the rate of the reaction will depend on the concentration of this, okay, alkyl chlorosulfide, whose concentration will again depend on the starting material, that is alcohol and thionyl chloride. Okay, therefore this is the rate law. We call it as rate law for SNi mechanism. Okay, now we'll see what happens if pyridine is added to this reaction. Okay, now I carry out the same reaction but in the presence of pyridine. Okay, then what happens? You are seeing that in the first step, in this step, HCl gas had escaped from this reaction. Now what happens when pyridine is added? Pyridine acts as a base. Okay, you know pyridine is a heterocyclic, okay, amine, heterocyclic amine, heterocyclic compound. It removes this, it reacts with HCl formed in this first step, HCl, and it removes this proton. Okay, and what do you get? You get here pyridinium chloride. You get here, this is called as pyridinium chloride. Now in the next step what happens? The Cl minus ion is now free, and what it does, this Cl minus ion, okay, what it does, in the first step this is formed, along with this HCl is formed. In the first step, even if the pyridine is there, the first step remains the same. You get here alkyl chlorosulfide, plus you get HCl. This HCl reacts with pyridine to give pyridinium chloride, and here this Cl minus ion now will attack this. Okay, this Cl minus ion will attack the alkyl chlorosulfide formed in the reaction from the back side. Okay, it will attack from the back side. It actually will be a SN2 now. In this case it will not be a SNi. In the presence of pyridine it will be SN2. Cl minus ion attacks from the back side, and you get again a transition state. You will get here a transition state. If I draw here, okay, to be right. This is backside approach of Cl minus ion. Okay, these three groups are in one plane, and this Cl and O minus S double bond O Cl. Okay, I can write it this delta minus, and also this is delta minus. Okay, if you observe here, this attack takes place from back side, and this Cl minus ion and this O minus, they are co-linear. Okay, this is the leaving group, O minus S double bond O Cl, O minus S double bond O Cl, and this Cl, they are co-linear, and these three groups are in one plane, as in the SN2 mechanism. This is SN2. Okay, if I write here, this is SN2, and finally what you land with, okay, I will write it here. You here Cl comes on this side, here this, okay, if I write here pH comes here, this is the CH, this is the hydrogen, and this is the CH3, plus these two electrons go here, plus S double bond O, okay, plus Cl minus. Okay, now what happens in the presence of pyridine? What happens? The first step remains the same. The alkyl chlorosulfide is formed and HCl is formed. But in the previous mechanism, the HCl gas escapes away. Whereas in the presence of pyridine, the HCl gets trapped. It reacts with pyridine, reacts with HCl to form pyridinium chloride. Now here the chloride ions are free and they now attack from the back side. They attack the alkyl chlorosulfide from the back side, and exactly a SN2 like mechanism takes place. Cl carries a delta minus charge, O minus carries a delta minus charge in OS double bond OCl, and these three groups remain in the one plane at 120 degree angle to each other. Okay, this is actually a SN2 transition state, and then finally the Cl gets attached from the back side and these groups leave away. Okay, these electrons shift here, the negative charge shifts here, okay, the negative charge shifts here, and Cl minus ion goes away. This Cl minus ion are represented here, this Cl minus ion are represented here, and this S double bond O here, and this product gets formed with inversion of configuration. If you see here, here it is Cl and here there is OH, this is inversion. So in the presence of pyridine, the reaction takes place with inversion of configuration. Whereas in the absence of pyridine, the mechanism which is taking place is as per SNi mechanism. In the absence of pyridine, it is SNi mechanism, whereas in the presence of pyridine, it is SN2 mechanism. Okay. Now, what are the evidence for the SNi mechanism? Okay. Now, there are certain evidences which have been given for SNi mechanism. It has been observed that the increase in the polarity of solvent, okay, for this reaction, increase in the polarity of the solvent for this reaction increases the decomposition of this alkyl chlorosulfide intermediate. Why? Because this intermediate decomposes, that is collapses to give carbocation, and carbocations will be definitely stabilized by polar solvents. Okay, polar solvents will stabilize charged intermediate. Therefore, increase in polarity leads to an increase in the rate of reaction, that is increase in the collapse of this intermediate. With this, I would like to end my session. Okay, I have completed the SNi mechanism. Okay, hopefully you would have understood this. If you like my video, you can subscribe to it. Thank you very much.